For this first problem, we're trying to find, we have a loop of current, and we are trying to find the distance d, and that the segment A, B will be at after current goes through this entire loop. Because we know it has a mass m. Due to the mass, it's going to have a weight. So it's mg going downward. But due to the current, if we apply the right-hand rule, we're going to have magnetic force have to be in the other direction. So at equilibrium, is equal to f of m or w weight. So that means IL, or I suppose we need cross V is equal to mg. From this bottom wire, in this region here, we are going to have a magnetic field that is pointing outside of the pole to the right hand pole. That means the magnetic field around AB is perpendicular to the current. Therefore, sine theta will simply be 1. So I don't have to worry about the cross product. That's just going to be IL B is equal to mg. What we're trying to find is the distance. We know that the magnetic field will be equal to mu naught over 2 pi d by the current. So which current is this? This is the current that is generating it, which is I10, which is the current through the bottom wire. In this case, it's the same, but in some other problems, it's not necessarily the same. So that is IL mu naught I over 2 pi V is equal to mg. Now, we know mu naught is constant, we know 2 pi, but we're trying to solve for d. G is also a constant, so we also know that. What we don't know is m and l, but we do know which is m over l. So we can simply do this equation for d first, which is IL mu naught I squared over 2 pi mg equal to g. Now, L over m is 1 over lambda m, which is equal to 1 over 0.1 times 10 to the negative 3 because it's in grams. This is 10 times 10 to the 3. Therefore, d is going to be 10 times 10 to the 3 times the current squared, which is 10 squared, times 10 to the negative 7 over 2 pi times 9.81, which is the gravitational acceleration. Therefore, I can put this, do this with 2. So that's going to be 100, 1,000. I'm really going to have to write this in a nice form. Times 10 to the negative 2. Oh, suppose we need these. And I'm going to do one more problem that I did do before. So we have two wires. First one's carrying current I1 is equal to 15 amps. Second one's carrying current I2. You can draw them in different colors. First one is green. Carrying current I1 is equal to 15 amps in that direction. Second one's red. Carrying current I2 is equal to 3 amps in that direction. And we're trying to find we're going to assume that this is our x-axis, this is our y-axis, positive x, positive y. Equation of the line is and the equation of the line that has no magnetic on it. Since we have two wires, these two wires are the XY plane. We just have to mention this in the XY plane. So we have two wires, and what we're trying to do is, so there is going to be a line somewhere along this XY plane, where if you go anywhere on that line, there's going to be no magnetic field. Now, the only way this is going to happen is if the magnetic field cancels out. So the magnetic field from the first wire is equal in magnitude to the magnetic field in the second wire, but opposite in direction. So the first thing we're going to do is split the plane, which is actually already split into 4 quadrants. I'm going to number them as 1, 2, 3, and 4. In each quadrant, we're going to go in the direction that each wire creates, the direction the magnetic field each wire creates. So the first quadrant, the green wire is going to create a magnetic field going into the quadrant. Left. The red one to the board. Out of the board. Now, for quadrant 4, there's no way that two vectors in the same direction are going to have signs. So we know that in the same, we could say the same thing about quadrant 2. So we know line does not pass through quadrant 4 and quadrant 2. However, since the magnetic fields are in opposite direction, there's a possibility for them to cancel out, but we want to see where they cancel out. So to see where they cancel out, we're just going to take an arbitrary point. Let's take this point here. Let's call this point A. A is going to be a distance x away from the y carrying current I2 and y away from the wire carrying current I1. So the magnitude of the magnetic field at A, magnitude of the magnetic field that's coming from the first wire, plus the magnitude, well, minus or plus in terms of vectors, or minus in terms of magnitudes. So all we have to do is say that the field from wire 1, well, B field, we use B for it, to the E field from wire 2. So that's simply, this, B field from wire 1 is going to be 2y. From wire 1, it's going to be y. There's a current, I1. Should be equal in magnitude. Remember, we're getting this magnitude here. 2 over 2.x. I1 over y should be equal to y2 over x. So the equation of our line. X1 is y is equal to I1 over I2x. That is y is equal to 15 over 3x, which is equal to 5x. So our line's actually going to look something like this. Well, I guess that's not accurate. This is going to be true. So we'll just have to make it pass through. Well, the slope doesn't really look like it's 5, but we can just measurements out of scale. So anywhere on this line, there's going to be no magnetic field because you can't see